Okay guys, so you already learned about the reaction rate as well as the collision theory. Okay, so your reaction rate can be increasing or decreasing by controlling several factors. Okay, so the factors that I'm going to talk about here is concentration of the reactants, pressure of the gas, volume of the reaction vessel, temperature, particle size, as well as catalyst. Okay, so in order for a reaction rate to increase or will be higher, you need to make sure there are more successful collision happens between the reactant molecules. So how to increase the number of successful collision is by controlling these several factors which increase concentration of the reactants. Okay, so increase pressure. Then increased pressure is related to decreasing in the volume of the gas or volume of the vessel. Okay, and third, increase the temperature. Okay, fourth or fifth, reduce particle size. Okay, and lastly, adding catalyst. Okay, I'm going to go through one by one variables afterwards. Okay, so how does increase the concentration of the reactants can increase the successful collisions and giving you a higher rate of reaction? Okay, when we increase the concentrations of the reactants, we will have more particles present. So when we have more gas particles that is present, that means there are higher chances of collision taking place between the gas molecules. Okay, so higher number of collision between the particles, increasing the frequency of successful collision, thus higher rate of reaction. Okay, so what about increasing the pressure of the gas? Okay, so when you increase the pressure of the gas, okay, these gas molecules will become close to each other. So higher pressure of the gas molecules become close to each other. So they are very packed in a container. So at a higher pressure, okay, so let's say this is the container. So the molecules are very packed towards each other, very close to each other. So they can collide vigorously with each other. So higher number of collisions that takes place between the gas molecules will result in a higher number of frequency of successful collision, thus leading to higher rate of reaction. These same concepts of increasing pressure also applies when we decrease the volume of the reaction vessel, because when the reaction vessel's volume has been decreasing, so the vessels become very high in pressure. So more molecules are close to each other, just like in this picture. So increase the number of collisions between the gas molecules, resulting in higher number of successful collision or higher frequency of successful collision, thus leading to the higher rate of reaction. Okay, so whereas in the terms of increasing temperature, it works in different way. Okay, it's not about in the numbers of collision between them, but in this one, increasing temperature leads to about the higher kinetic energy, because when you are increasing the temperature of the systems, okay, when you increase the temperature of the system, this will cause average kinetic energy of the molecule to increase. Okay, so average kinetic energy of the molecules, each of the reactant molecules will increase. So when they increase in kinetic energy of the molecules, so increased number of molecules having Ke greater than activation energy, because just like in the collision theory that we talked in the previous video, for a successful collision to take place, there must be two requirements that need to be fulfilled, which is the first one, you need to make sure the reactant molecules have kinetic energy equals or greater than the activation energy of the reaction, and secondly, they must collide in the correct orientation. Okay, colliding in the correct orientation is a kind of a variable process. That means it varies depending on the reaction systems. It's not something that we can control, but kinetic energy for the reactant molecules to have equal or greater kinetic energy, then activation energy is something that we can control by giving more heats to the reaction system. So more molecules will have greater kinetic energy. So some of the molecules might have enough kinetic energy to overcome the activation energy, thus resulting in higher number of successful collision. So if we want more successful collision, that means we need to make sure more molecules having enough kinetic energy to overcome the activation energy. By how? By just increasing the temperature of the system. Okay, so this increasing in temperature can be explained in the Maxwell Boltzman Distribution Curve, which I'm going to tell you later towards the end of this video. Okay, decreasing particle size. This particles is referring to the reactant molecule size. Okay, so if let's say if you go to the kitchen and you want to cook beef, okay, cook beef or cook chicken. Okay, so you're going to chop the chicken into very small pieces. Okay, if we try to compare, okay, between a minced chicken and a cube chicken and a whole chicken, okay, definitely the minced chicken will cook fastest, okay, followed by the cube chicken and the whole chicken, because in the minced chicken it has the smallest size. Okay, smallest particle size, that means it has the largest total surface area. It means it will have a larger exposed area for the reaction to take place, leading to a higher number of successful collision, leading to a higher rate of reaction. So that is what happens when you reduce the particle size. Okay, so okay, so what I compare just now, okay, I comparing is in the terms of cooking minced chicken versus cube chicken and the whole chicken. Okay, so minced chicken takes the shortest time to cook because it have the smallest particle size. That means greater surface area. Okay, the greatest surface area. Okay, leading in higher frequency of successful collision and higher rate of reaction. Okay, so that is live examples on how we decrease the particle size can lead to the greater rate of reaction. Okay, and what about adding catalyst? Okay, so what is a catalyst? So catalyst is a special substance. Okay, a special substance that speeds up a chemical reaction, okay, by providing an alternative pathway with lower activation energy without itself being confused. Okay, so this is the definitions of catalyst. Okay, so this definition of catalyst you need to memorize. Memorize this exactly on how I write this definition. Okay, so it must consist of these 3 points for you to obtain full marks for your definitions of catalyst. Okay, so additions of catalyst will lower the activation energy, okay, in your chemical reaction. So activation energy can only be explained by drawing energy profile diagram. Okay, so I have here energy profile diagram for my exothermic reaction. So this is exothermic reaction. Okay, so in this one, okay, I labeled here with 2 different activation energy value. Okay, so this is the first one, EA1. Okay, so EA1 is referring to the activation energy without catalyst. So this is activation energy without catalyst. That means the original one. Okay, as you can see in my sketch, this dotted red line is referring to the new routes, okay, for the reaction with a lower activation energy. So it has a smaller EA. So this EA2 is named as the activation energy with catalyst. Okay, as you can see, the activation energy with catalyst is smaller. Okay, EA2 is smaller than EA1. Therefore, more molecules, more reactant molecules have enough kinetic energy to overcome the smaller activation energy, resulting in a greater number of successful collision, leading to a higher rate of reaction. Okay, so catalyst is a special molecules. Okay, so normally the catalyst that being used in a chemical reaction comes from the transition metals, transition elements, okay, in your transition elements period, such as iron, titanium, vanadium, okay, and so on. Okay, so this catalyst does not being consumed in the reaction, so it does not interfere with the chemical reaction. It just helps to speed up the chemical reaction by providing a new pathway with a lower activation energy. So how are you going to explain the effect of adding catalyst towards increasing the speed of reaction? By giving the definition of the catalyst, okay, this long definition, and secondly, draw the energy profile diagram. So if the reaction is exothermic, then draw energy profile diagram for exothermic reaction. But if the reaction is endothermic reaction, that means you have to draw energy profile diagram for endothermic reaction. If the question does not state any, okay, so you can pick any of this energy profile diagram, and in the same energy profile diagram you label two different activation energy, okay, just like in my examples here. Okay, I'm labeling the first one, the activation energy without catalyst, EA1, okay, so it's bigger, larger value, and I label in the same energy profile diagram is the new activation energy with catalyst. Okay, so the concept here, you must label with or without catalyst for the value of activation energy in the same energy profile diagram, so that people can see clearly what will happen when we are adding catalyst. Okay, again, just to remind you, catalyst will never interfere with your chemical reaction. So we're going to find the suitable catalyst for the chemical reaction, and normally the catalyst comes from the transition metals, either transition metals or the transition metals compound. Okay, just now I already talked about how increasing temperature will lead to a higher rate of reaction. I already mentioned about Maxwell Boltzman distribution curve. So your Maxwell Boltzman distribution curve is a special kind of curve which it shows the variations of kinetic energy of the molecules at different sets of temperature. So in the same kind of sketch, I can have more than two temperature. So in these examples given here, okay, so in this one, I only have a Maxwell distribution curve which shows two different sets of temperature, which is T1 and T2. Okay, so my T1 is a small lower temperature compared to my T2. Okay, so the first curve here, okay, so the green line here is referring to the distribution curve at T1, a lower temperature, such as if I have here 150 Kelvin. Okay, and the second one, okay, so the purple line here, purple curve here, is referring to my distribution curve at T2, which is a higher temperature compared to T1, and let's say my T2 is about 450 K. Okay, so in my Maxwell Boltzman distribution curve, okay, it will consist of y-axis, which represent number of molecules, okay, and on the x-axis is referring to the collision energy. Okay, as you can see in both of the curve, okay, so there are peaks. Okay, so this peak represent the highest number of molecules present at that time. Okay, so the greatest peak here and the greatest peak here at T2, okay, it indicates that most molecules, okay, most molecules occupy this area, occupy at this area which is at this value of energy. Okay, so these two peak. Okay, so that means at 150 Kelvin, which is your first peak, okay, you're at your T1, okay, mostly, okay, most of the molecules at T1 has this average kinetic energy at E1, okay, whereas at 450 Kelvin, okay, most of the molecules are having average kinetic energy at E2, okay, so as you can see, E2 has a greater amount than my E1, okay, that means at higher temperature, okay, at higher temperature, average kinetic, it will increase the average kinetic energy of the molecules. So more molecules will have greater kinetic energy or equals to the activation energy, resulting in higher frequency of effective collision or successful collision and higher rate of reaction. So how does this Maxwell Boltzman distribution curve showing the number of successful collision? Okay, so this is the activation energy of the reaction. Okay, so under the peak T1, okay, which is the shaded area in yellow here, so this shaded area is referring to the number of successful collision at T1. Okay, whereas at T2, I will have a greater number, which is represented by this area. So this whole area is the number of successful collisions at T2. Okay, as you can see, the shaded area at T2, higher temperature is greater than the shaded area at T1. That means, okay, more successful collision is taking place at higher temperature. So increasing temperature, as shown in the Maxwell Boltzman distribution curve, that shows that the average kinetic energy of the molecules is increasing. Okay, so it is how? By looking at the peak of the curve. Okay, so peak is at a higher energy when you are having a higher temperature, okay, and in the same time, and in the same Maxwell Boltzman distribution curve, also you can see a greater number of successful collision is taking place at higher temperature. Okay, that means more molecules is having in more kinetic energy to overcome the activation energy, so resulting in higher rate of reaction. So in this example, I have comparing between two different temperature, which is one at 150 Kelvin and another one at 450 Kelvin. Okay, so this my sketch here for Maxwell Boltzman distribution curve is okay, so in my Maxwell Boltzman distribution curve here, I'm comparing, okay, how does a curve look like at two different sets of temperature, which is 150 Kelvin and 450 Kelvin. Okay, so in the same Maxwell Boltzman distribution curve, we can show the variations in the kinetic energy of the molecules at more than two different temperature. For example, in this one, okay, I'm comparing in between three different sets of temperature. Okay, as you can see again, okay, so let's say this is the activation energy for the chemical reaction. Okay, so these three different peaks, okay, so this is the first peak, second peak, third peak, represent the greatest number of molecules have that average kinetic energy. So according to the 100 Kelvin, so most of the molecules is having average kinetic energy of E1. Whereas in my second curve, which is at 250 Kelvin, most of the molecules at this temperature will have average kinetic energy equals to E2. And at 350 Kelvin, most of the molecules will have a kinetic energy at E3. Okay, so as you can see, the value of the kinetic energy, E3 is the greatest, followed by E2 and E1. Okay, so that means higher temperature, okay, leading to higher average kinetic energy of the molecule. Okay, so that means, okay, increase number of molecule having Ke greater than activation energy. So how I'm going to prove that? By looking at the shaded area for the molecules that pass kinetic energy more than the activation energy. So this yellow shaded area is referring to the number of successful collisions at 100 Kelvin. So this one is number of successful collisions at 100 K. Okay, so when it is at 250 K, it will cover this larger area. So okay, this blue region, okay, so this is when we are number of collisions at number of successful collisions at 250 K. So that means at higher temperature, you will have a greater number of successful collision as shown in this shaded area. Okay, so Maxwell Boltzman distribution curve is a very important curve in order for you to explain about the effect of changing temperature towards the reaction rate. Okay, so we already discussed about factors affecting reaction rate, which you can control by changing the concentrations of the reactants, okay, increasing the pressure of the systems by either by increasing the pressure or decreasing the volume of the vessels, okay. Thirdly, by adjusting the temperature. Increase the temperature will lead to a higher rate of reaction. Lowering the temperature will lead to a lower rate of reaction, and that one you can explain by drawing Maxwell Boltzman distribution curve. Okay, and then we already talked about how we decrease the particle size to increase the rate of reaction. So I already explained in the terms of cooking on how we comparing the times taken for minced chicken to cook with the cube chicken and whole chicken. So smaller particle size means smallest one is the minced chicken, which have the smallest particle size and largest total surface area, leading to a higher rate of reaction. Thus require the smallest time for the chicken to cook. Okay, and then we already talked about additions of catalysts. So to explain about additions of catalysts towards the rate of reaction, you need to draw energy profile diagram. So in the same energy profile diagram, you need to compare, okay, on the curve the activation energy without catalyst, and when we are adding catalyst, what will happen to the activation energy. Okay, so you learn two different curves throughout this video, which is your energy profile diagram and Maxwell Boltzman distribution curve. Okay, so that's all for today. Thank you for watching.